This is Dr. Staley in voiceover because the lapel mic didn't work when I first recorded this. When you are working in the lab and you have glass, especially when you have glassware that's easy to tip over, it's important to make sure that your movements are not jerky. So if you are in a hurry to do something, you need to not concentrate on moving quickly, but rather on moving very, very smoothly. The reason for this is that uh, if you tell your limbs to move very smoothly, then as soon as they touch something, your automatic reflexes will kick in and they'll stop. But if you tell them to move very quickly, then your automatic reflexes will not, click in as easily, and you're much more likely to accidentally knock it over. And by knocking things over, you can not only break stuff, but also you end up having to clean stuff up and make solutions a second time, and that takes up even more time. So even if you were concentrating on going fast, you could get done soon. It won't even work. Anyway, this is the experiment where I'm making the calibration curve for the absorption spectra for uh, a nickel sulfate salt. Now, you can see I've got some beakers here and some volumetric flasks. The beaker in my left hand contains nickel sulfate hexahydrate. I've weighed out an appropriate amount. I've weighed out the appropriate amount to put in the first volumetric flask. The exact amount is in the PDF that I put online. Now, ideally, you would want to dissolve it in the volumetric flask itself. But the issue there is that I weighed this out by difference, and pouring that directly into the flask, I run the risk of course, having some stick to the outside. This is especially problematic because of static electricity. Static electricity can cause solids to stick on the rim and, of course, go onto the outside of the rim. So what I'm trying to do is I'm trying to do a quantitative transfer. So I'm trying to transfer the whole thing by first dissolving it in the sulfuric acid that I'm going to use for the dilutions later. And then I'm going to pour that into the volumetric flask. The key here is to make sure that I use a lot less sulfuric acid than the volume of the flask, because if I use more, well, I can't really take anything out then, now can I? Anyway, so you see that I have 4 volumetric flasks here. Now the deal is that we're doing a 4-point calibration with 4 different concentrations. With this, so in order to do that, we're going to do a serial dilution. So first, I take the amount of nickel sulfate hexahydrate, dissolve it, and pour it into the first flask, and I dilute that up to the level. Up to, this one is a 50 milliliter flask, and I have in here slightly more than 1 gram of the salt. Now, with a serial dilution, what is going to happen is that I'm going to be taking a known amount out of this flask. I'm going to be taking 5 milliliters of solution out of this flask. See, the whole thing is dissolved now. Now I can pour it in. What I'm going to be doing is I'm going to be taking 5 milliliters out of this flask, putting it into the next one, and diluting that up to 25 milliliters. So each of these is going to be a 5-to-1 dilution. I'm going to end up with 5 times the volume of what I transferred in. As a result, the concentration is going to go down by 5-fold each time also. Here I've marked this flask as my primary standard because this is the flask where I have not done any serial dilutions yet. Now you see, before I pour any sulfuric acid directly into the flask, I'm rinsing out the beaker that I had my salt in to make sure that any droplets that might contain even a little bit of that salt that might be on the edge or on the bottom of the beaker are washed into the flask also. That way I know exactly how much nickel I have in the flask because I weighed it out. There we go, pouring it in. And here I'm pouring in some more sulfuric acid. And here I've crouched down so that my eyes are very close to the level of the marking on the volumetric flask. I'm done here. So you can see I've got slightly over the mark on the flask. It's maybe a millimeter or 2 millimeters above the mark on the flask. So I've decided that I'm going to leave that in there, and part of any discussion is going to discuss what that is going to do to the error, how that is going to change the error of the calibration curve. Now, here I'm using a volumetric pipette to transfer the solution out. This is 5 milliliters that I'm putting into a 25 milliliter volumetric flask. That's right next to the first one. Now, one of the things that I want to point out here is normally you would not simply label these flasks as primary standard and dilution 1, dilution 2, dilution 3, etc. Normally you would also include on the label what solution is in there and what the concentration of the solution is also. I'm not doing this because I'm leaving that as part of the exercise that I want all of you to do. And here I'm showing you the tip and how there's some solution left in. This volumetric flask is meant to deliver 5 milliliters exactly if you leave some in, so you don't blow it out. That is, you don't blow it out into the receiving flask. You blow it out into a waste beaker instead. I'm putting that down, and I need to dilute this up to 25 milliliters. So one of the things about this is that because this flask has a neck significantly more narrow than the other volumetric flask, I don't want to risk pouring directly from the beaker into there because I'll be more likely to spill things. So instead, I'm using the funnel to pour it to pour in the sulfuric acid instead. And getting back down so I can see it more accurately. There I go, pouring it. And I'm lifting up the funnel every now and again, because with a lot of these funnels, sometimes the acid can get in between the neck of the funnel and the neck of the flask and form droplets there. And I want to make sure that I get everything down so that I can see where the level is, where the level of the solution is. There. Now I've got as close as I can comfortably with the funnel, so I'm going to finish this off with an eyedropper instead. This eyedropper has been cleaned, and since cleaning it has only touched this solution of sulfuric acid, so that I don't need a separate cleaning step. There we go. There's my solution, and it is right at the line this time. That is, the bottom of the meniscus is right at the line, I mean. Yeah, so I filmed this on my the webcam that's attached to my laptop, so I can't always tell when I've put the flasks close enough to the camera to accurately show where the meniscus is. And as you can see, even though I blew out the tip before, there's now a little bit of liquid back at the tip. That's because some solution was on the sides of the pipette, and so it, of course, went down to the tip because that's where it was pulled by gravity. But one of the things about this means that I now have that higher concentration solution, the non-diluted solution, the primary standard solution, on the inside of the pipette. So what I need to do is I need to bring up this new solution into the pipette, then push it down, push it back up, push it down, push it back up for a little bit, so that I make sure that any effect that might have on the concentration is that, having tiny droplets of the old solution on the concentration, I need to make sure that any effect of that is diluted and negated as much as possible. And it'll be diluted more if I mix it with 25 mils rather than with just the 5 milliliters that this pipette holds. So that's what I did, and then I transferred 5 milliliters to the flask labeled dilution number 2. Now, the primary standard has its concentration. It is the highest concentration nickel solution here. Oh, got a little acid on the paper towel. So the primary standard is the largest concentration solution here. The first dilution is 1/5 the concentration of the primary standard because it's a 5-to-1 dilution. This is now going to be a 5-to-1 dilution of the first dilution, so it's going to be a 25-to-1 dilution as compared to the primary standard. And there's the finishing up with the funnel there, and then now I just bring it to the top of the line with the eyedropper. That's at least close enough that you can see the bottom of the meniscus is right at the line. And then dilution number 3. And doing the transfer one more time. Now after I'm done with this transfer, originally I tried to film a lot of what I was doing on the computer, and I kind of went at length on a lecture about it, but because the lapel mic turned out to not actually work, I couldn't record that lecture, and in looking over the footage, it's kind of hard to see what I'm doing on the computer. So I decided to not include that in this. I decided to edit that out because it's just kind of boring watching someone sit around and talk with no sound and typing on a laptop. But that's just basically what. So just pretend that I've showed you turning on the laptop and turning on the spectrometer and opened up both the application that runs the spectrophotometer and also opened up an Excel file and prepared it so that I could put in all of the data that I get. Now, if dilution 1 was a 5-to-1 dilution as compared to the primary standard, dilution 2 was a 25-to-1 dilution as compared to the primary standard, then dilution 3, which is another 5-to-1 over dilution 2, is going to be a 125-to-1 dilution over the primary standard. So this is a very, very dilute sample here. Okay, there we go. Now in my left hand you can see the cuvette that we're going to use for the spectrophotometer. That's where the sample is going to go in and where we're going to pass light through and see how much of the light is absorbed at each wavelength. However, before we can do that, we first need to run a blank solution. A blank needs to have everything in it except for the one thing that you want to actually study. Now in this case, the solutions that we're looking at are all they have nickel sulfate. The nickel sulfate has hexahydrate. It is a hexahydrate, so each cluster has 6 water molecules in it, but it's being dissolved in water also. And the water that it's being dissolved in has sulfuric acid. So basically, what we've got is we've got nickel ions, sulfate ions, and water. And, some hydronium, of course. Which means that the blank needs to have sulfate ions and water and a bunch of hydronium. So we're just using sulfuric acid as the blank solution. Now here I'm showing that the cuvette is very clear and very transparent on all 4 of its sides. Some cuvettes are not that way. Some cuvettes have 2 very, very transparent sides and 2 kind of low quality sides. So you need to always be careful to check that. Also, I wipe this off with a Kim wipe. Kim wipes are basically small paper towels that don't have lint. So that way I make sure that I'm getting rid of any water droplets that might scatter the beam and cause more what looks like absorption that isn't actually absorption. So that way the readings are consistent. Now this is what the sample chamber on the spectrophotometer looks like. The cuvette goes in there. There is usually some sort of a ball bearing on a spring or something similar. Sometimes it's a piece of metal that's bent and has a lot of spring to it that holds it in place. On the left-hand side is where the light comes out. On the right-hand side is where the detector is. And so here I'm putting the laptop back down so that I can go ahead and close the lid. Now, when I take a Now, before we actually go to do the measurements to get the data points for each concentration, we're going to need to figure out which peak we're going to use, which wavelength we're going to use that's going to have the highest absorbance and therefore give us the most accurate, most reliable data. So first, we need to take a whole spectrum, and that's what I just did with the blank. I told the spectrophotometer to take an entire spectrum going from 350 nanometers to, I believe, 700 nanometers. And now I'm going to take a spectrum with the primary standard. So remember what I said about being very careful about droplets that might be coating the walls of a pipette before? Well, you have the same problem with the walls of a cuvette like this one. So before I actually add the primary standard that I intend to take a spectrum of, I first need to put a bunch of solution in there so that any drops or droplets that are inside the cuvette I know are drops or droplets of the primary standard. When you've got a bunch of drops in there that are just the blank solution, anything else that you add is going to be diluted. I don't want that. So I rinse it out with some of the solution I intend to use. I'm shaking it, I'm moving it around to make sure that the solution properly coats all of the insides of the walls of the cuvette. Anytime now. I toss it, and then I add my solution. Now, one of the things I'd like to point out here is that I'm using the volumetric pipette because that's the only piece of glassware I have here with a long enough neck to reach all the way down to where the solution actually is in that volumetric flask. But I'm not actually delivering 5 milliliters. The reason I'm not delivering 5 milliliters is because these cuvettes do not hold 5 milliliters. So in this case, I don't need to have the solution all the way up to the line. I just need to have enough in there to fill the cuvette, and then I can put the rest back in my flask. Anytime now. So here we go. Got the cuvette, wiping down the outside. Also, one thing about this is I'm wearing gloves, which means that I'm not leaving fingerprints on there. If you are touching this with your bare fingers, you can, but you have to make sure to wipe off your fingerprints because that is also droplets of water. that can scatter the light. There we go. So now that I'm actually taking a full-on spectrum, I have to tell it, to take the spectrum and that this is the real deal. And what I'm having it do is I'm having it take 5 spectrums so that, I have it do the spectrum 5 times in a row, just to make sure that any minor errors in the spectrometer itself will show up as a bunch of funky, really, different numbers. Da, da, da. And so here I'm telling the software to look for the peaks and to help me find the actual peaks. Now you'll notice that there's like a U shape on the screen. That's because the default for the display is basically zoomed in too much, where the vertical axis is too small. So I'm just kind of guessing where it should be in order to show the actual peaks. And when I have it do it again, there we go. So in the new display, I can see that there's a peak that's just below 400 nanometers. I'm using the software to identify what that peak is, like the exact tip top of the peak. It comes out to 394.5 nanometers, but unfortunately the software will only let me take future scans at wavelengths that are in multiples of whole numbers of nanometers. Now, there is another smaller peak out near the longer wavelengths, but I'm not using that because the absorbance is much lower there. I want to use the peak where the absorbance is the highest because that's going to give me the most precise data when it comes to applying Beer's law and trying to figure out the concentration reason. Anyway, here I'm talking about a problem that I had with running the calibration curve on the nickel sulfate salt the first time, where the two most concentrated uh, solutions lined up like I was expecting, but then the last two solutions were flipped, where it's normally supposed to go from high concentration, high absorbance to low concentration, low absorbance. It went high, low, lowest, and then up again. So I'm trying to redo the calibration curve because you can't just redo one data point that you don't like. You have to redo the whole thing. It's not honest otherwise. So I was thinking that there were 3 possibilities that I could use. One possibility was that I could have had stray light coming into the spectrophotometer. That would have gone onto the detector, and so the measured absorbance would have been much lower than the actual absorbance. If that happened with the third sample, the sample labeled dilution 2, because the samples were primary standard, dilution 1, dilution 2, and dilution 3. If that happened with dilution 2, then that would explain the problem. I don't actually think that that was the problem, though, because if you look at the spectrophotometer, it's got that lid right there that my hand is on right now, and that's pretty simple to just close down. So I don't think that that was actually the issue. The second problem that could have been the issue is that perhaps there were bubbles in the cuvette that I did not notice. Now, if this happened in the most concentrated solution, in the least concentrated solution, then it would have scattered light, and then less light would have hit the detector, and that could have looked like absorbance to the detector. Sorry, that would have been recorded as extra absorbance by the detector because it's light that's not hitting it. So, um, I'm redoing it, making sure to flick all the cuvettes to get all the bubbles out. The third possibility is that I could have been running straight into the limit of quantification. Now, the limit of quantitation, I think it's the limit of quantitation. At that limit, the detector can still detect that there is light coming through and that there's absorbance, but it can't give you an accurate measure of the absorbance. The absorbance here, however, went from about 0.017 absorbance units up to about 0.06 absorbance units. And I would expect this detector right here to be accurate down to 0.001. So I don't think that that's very likely. So I think it's more likely that there was just bubbles in the cuvette that I need to be careful to get rid of. Right now I'm running the blank for the new calibration set. I'm labeling this blank. I'm labeling this calibration curve. I'm labeling this calibration curve, and the operator that I put down is section 04 because that is my Chem 200 section. Here I'm removing the blank and disposing of the sulfuric acid in a benchtop waste container. And now, what I need to do before I add the primary standard solution is I need to rinse the cuvette with some primary standard so that any droplets that are left in there are the same have the same concentration of nickel as all the other droplets, as the bulk solution that I want in there. If you don't do this, then you end up mixing the solution that you're putting in with whatever drops or droplets of the previous solution that was. In this case, that would force the concentration to go down below what I calculated, and thus would throw off the calibration curve. Here I am remembering that I don't actually need to get a full 5 milliliters into the volumetric pipette. I'm using a volumetric pipette in order to get the solution out of the volumetric flask because the flask has such a long neck. If I had a Pasteur pipette handy, which also had a long neck, then that would be probably more ideal, but I don't happen to have one of those lying around, so I'm using the volumetric pipette instead because it's long enough to reach all the way down to the bottom, whereas the eyedroppers that I have are not. And here I'm wiping off the sides of the pipette to make sure that I don't have any solution on the sides. I don't want to contaminate, and I'm getting rid of the bubbles by flicking it. Yeah, I don't want to contaminate the inside of the cuvette holder. That won't be nice for my next few measurements, and it won't be nice for whoever uses this spectrophotometer after I do. There we go. So I've got one data point down, 3 more to go. Here I've disposed of most of the solution into the waste container, and I am getting out the pipette again. And once again, remembering to pipette some of solution out. So the first data point went down as primary standard. This is going down as dilution 1. Rinsing the cuvettes. There we go, the cuvette is being wiped down. Once again, make sure that there's nothing on the outside. Put it in, put it down, and take the next scan. Dilution number 2. So this one is where I have to start being really careful, because there's a problem either with dilution number 2 or dilution number 3. Well, diluted solution number 2 or diluted solution number 3. So I need to make sure to rinse it out and then fill it up, and then make sure that there are no bubbles or anything in it, and that there's nothing on the sides. I want to reiterate here what I said when I made these solutions in the first place. Normally, what I would do is I would label the solutions with the actual concentration of the important chemicals in them, but I'm leaving that to all of you to calculate on your own. You know, it's not very descriptive to say primary standard dilution 1, 2, and 3. And just a little bit more to top it off. And remembering to wipe off the cuvette before I place it into the spectrophotometer. And finally the last one. Rinsing it out, then adding the sample. And there we go, getting the final data set. There. Okay, so this data set turned out pretty good. Here the data is fairly linear. The most concentrated to least concentrated, primary standard to dilutions 1, 2, and 3. Their absorbance goes 0.36 absorbance units, 0.13 absorbance units, 0.037 units, and 0.0176 absorbance units. Now, remember the amount of nickel sulfate hexahydrate. That's with 6 water molecules for every nickel sulfate cluster that had 1.0015 grams in it, and the initial dilution was 50 milliliters.